Hello everyone, I hope you are doing well. So in this video, we're going to discuss the first 4 problems of CodeTON round 5, which was rated for both division 1 and division 2. So you can see still there is almost an hour left, and I was able to solve the first 4 problems, and even after there is much time remaining, I have lost all hopes for problem E. I feel like it's a very difficult mathematics problem. So anyways, for today's contest, I felt like the problems were a bit different. I don't know, it's just me, or for the past few contests, I felt that the first two or three problems were a little bit difficult in the sense they were not very direct. But in today's contest, the first two problems were very straightforward and direct, and you could have solved it easily. So we're going to discuss the first 4 problems, and let us quickly start with the first problem. So in this particular problem, basically if you just read the whole statement and try to condense it, it reduces to the form that you have been given two arrays, and you have to calculate the sum of both the arrays, and whichever one of them is greater, and you will have to print them. So how do we actually reach to this particular conclusion? Let me just take this particular part. So we'll take this one, right? So this is a very long statement, and from this long statement, we had to derive the conclusion that we just had to calculate the sum of the arrays, right? So how do we do that? You see that we have all of these values, right? And they both are making some moves. So if the first player has a monster X and the second player has a monster Y, so this monster's ability will get reduced by Y, so it will be X minus Y, and this monster's ability will get reduced by X, so this will be Y minus X, and at least one of them will become 0, obviously. In that case, if let's say this monster becomes 0, then it will be removed from the game and his health or his ability will be reduced to X minus Y, right? Now the second player, this is P2, let's say this is P1. So the P1 will still have this particular monster with him, and player P2 will find a new monster to compete in the battle with. So each player will throw their monsters, right? So basically the total health that player 1 has will be the sum of the abilities or sum of the healths of his monsters. So basically if the array 1 has A1, A2, A3, A4, A5, A6 and so on, so his total health that he will have will be equal to the sum of all these values, and the total health the player 2 will have will be equal to B1, B2, B3, B4 and so on, right? So if we calculate the sum of both of the values, so if the sum of values of A is greater than sum of values of B, then player 1 will win. Otherwise, if it is less than, player 2 will win. Otherwise, it will be a draw, right? So this is what you will get when you try to condense this statement, right? So let us have a look at the code now. So you will see what I have done is I have taken two integers n and m, and I create two values x and y. So basically these are the number of monsters player 1 and player 2 have respectively, and x and y is going to be the sum of their values. So initially both of them are 0. So I take the first n values as input and I add them to a, and I take the first m values as input and I add them to y. So if x is greater than y, I print player 1. If y is greater than x, I print player 2. Otherwise I print draw. So this was all about the first problem. Now let us have a look at the second problem. So this particular problem says that we have been given 3n books, right? And those 3n books have been arranged in form of stacks. So what we essentially have to do is there is a value x, right? And whenever we read a book, we will read it from the top of the stack. So at each moment of time, we will have three options, right? Either we choose from the first stack, or we choose from the second stack, or we choose from the third stack. Whenever we read a book, our total knowledge will become equals to u or v. So u is the initial knowledge that we have, and v is the knowledge gained by reading that particular book, right? So each of the books have some value. Obviously at each time, as I have explained, we will only pick a book from the top of the stack, so we can only take the first book and then the second book and so on, right? So we have to tell whether we can choose the books in some way such that the total value becomes x, right? So let me just explain you this particular thing with the help of a demonstration. So let's say you have some, let me create three stacks first. So let's say this is our first stack, right? And we will have a similar second stack, and again a third stack, right? So we will, let's say we have three stacks like this. So let's say my total value is in the first example it is 7. What if I try to write the binary value of 7, right? So it will be equal to like this. right? So if I'm choosing books from any of the stacks, I'll have to choose some p amount of books. Let p be any integer, right? By this I mean I can take only books from the top. So if I want to take this particular book, I will have to take all the books before it, right? So similarly for any other stack, if I want to take this particular book, I will have to take all the books above it. So whenever I am taking all of these books, the value that these books will contribute to my answer will be the OR of all these values, right? And since I want my answer to be 7, I would not want any bit that is not set in 7. So for example, there are only 3 bits that is set in 7, that are these 3 bits. So if any of those books is giving me a knowledge of 8, let's say, so 8 is represented like this, right? So if any of those books is giving me a knowledge of 8, that means I don't have to take it, because if I take it, my OR value is never going to be 7, right? Because this bit will be set in it. I can only take the books only when either the second bit is set, or the first bit is set, or the 0th bit is set, right? So if I know this fact that I can only take the books in which either of these 3 bits is set, right? It can be like 110, 010, 101. I can take these. This is okay, but I cannot take a book in which a bit is set, let's say fourth bit is set, which was not set in the value of x, right? So for each of those 3 stacks, I will know what is the maximum number of books I can take, right? So I can take the first book only if there is no bit in the first book that has a bit set other than these 3 bits, right? So for each of those 3 stacks, I will know what is the maximum number of books I can take, right? So let me just greedily take all of them, right? So if I can take, let's say, a number of books from here, b number of books from here, and c number of books from here, I will take all a books, b books, and c books respectively. So let's say these books contribute value 1, these books contribute value 2, and these books contribute value 3. So this is the maximum contribution I can have from all the 3 stacks. If the OR value of these 3 values is equals to 7, or the value of x, then my answer will be yes, otherwise my answer will be no. So what I am trying to do is, let me just write it more in a more concrete manner. So the first point is, first observation, the most important observation, I cannot take any book which has a bit set and that bit is not set in the value of x, right? This is my first observation. Now what I do is, I try to take the maximum number of books from each stack, right? If I cannot take a book, that means I cannot take any more books from the stack. But what do I mean by the third point? If I cannot take the ith book in the stack, right, in any of the stacks, then I cannot take the I plus 1th book from that particular stack. Because to take the I plus 1th book, I will always have to take the ith book, right? I can only draw books from the top. That is why if I cannot take the current book, that means I cannot take any more books from the stack, right? So now what I do is, I greedily try to take the maximum number of books I can, right? So once I have done this, I calculate value of OR from all books taken, right? So this would be my final approach for this particular problem. Now if this final value of OR, this final value that I have calculated, is equals to the value of x, if it is equals to x, then my answer will exist yes, otherwise it will be equals to no, right? So let us have a quick look at the summation. So you will see what I have done is, I have taken 2 integers n and x, and I have created a double dimensional vector size 3 cross n. So 3 is the number of stacks and n is the number of books that we have in each stack, right? Now I just go through all the 3 stacks and I just take input it on all of the 3 stacks. So now what I do is, this is just my valid function, we will come to it in a little while. First I have initialized my answer with 0. So now what I do is, I go through all the 3 stacks, so from I0 to 3, now I calculate the value of take. So take is the value that I can take from the current stack. Now I try to traverse through all the books in that particular stack. If the current book is a valid book, right, I will tell you about this valid function in a while, but if the current book is a valid book, I take the current book, otherwise I just break. right? So this is what I'm doing. I'll take this value of take, that is the value of all the books that I have taken till now, and I'll calculate the bitwise OR with answer. So at the end, if answer is equals to x, I'll print yes, otherwise I print no. Now let us discuss what is the valid function. So I will receive the value of the book P in this particular function, and I just traverse through all the 32 bits. Now I check if the current bit is set in my value of P and it is not set in the value of x. From here I can directly return 0. Otherwise, if none of the bits are like this, I can return 1 at the end, right? So this was all about the second problem. Now let us have a look at the third problem. So the third problem was interesting DP problem. So let us have a look what it says. So the problem statement is pretty straightforward and small, unlike the first problem. So this problem says that we have n balls arranged in a line. Now the color of the ith ball from the left is ai. So basically we have been given some balls and each of them is associated with a color. Now what we basically can do in this particular array is we can choose two indices I and j such that they are not equal, and if the values at those two indices are equal, then we can remove all the elements starting from I to j, right? Both of them will be inclusive. Now we have to find the maximum number of balls we can remove. So let me take this particular example, first example. So what we are essentially doing is, let's say, let's say this is the values that we have, that is 1, 2, 2, 3 and 3. So if I choose this particular 2 and this particular 2, I can choose this particular range and remove all of them, right? So if I remove, the remaining values will be like this. Now if I choose this particular ranges, then I can remove these two and the only remaining value will be 1. So my answer is 1. Now let me just give you one more example from myself. This is one example that I was thinking about during the contest, and let me just write, let's say there is 2 here, there is 1 here, and there is 2 here. There are some elements in between. There is one element in between here. There is 3 and then some elements, and then there is 1, then 3 finally, right? So these are some elements. We will now discuss the number of elements or what are the elements actually, and let's say there is one element in between here, right? So now what I do is, the first thought that when we look in such type of questions is, can I apply greedy to it, right? That is why I am discussing this particular problem, to show you that we cannot apply greedy and why we cannot apply greedy. So one of the greedy approaches can be, let us take the maximum size of the segment that we can remove, right? This is one of the good greedy thoughts. Now if I take the maximum size, that would be 1, right? So these two ones are including a lot of elements in between, right? So this might be a probable answer, and at the end we will be left with 2 and 3 at the corners. So in this case we are left with 2 elements, right? Now let us have a look at another case. What I can do is I can choose this particular 2 and this particular 2. So all the elements between these two elements will be removed. Then I can choose this particular 3 and the last 3. So all the elements between these two ranges will be removed. The only element remaining would be this central element, right? So the answer is 1 in this case. That means greedy is not possible. The most simple greedy thought failed in this particular test case, and from here I knew that greedy is not possible in this particular problem. Now let us try to solve it with DP. What are going to be the DP states? Let us discuss that first. So my DP states are going to be, let's say I am denoting my DP of ij, right? So DP of ij, in DP of ij, I will be the ith ball, let's say, right? And j is going to be of size 2, right? 2 size, let me write. So what are these going to denote? So let's write j is equals to 1. So if j is equals to 1, that means I want to include this ball at the ending of a sequence. So basically what I mean by this is, I want to use this ball and I want to use this as the ending part. So we are like creating ranges, right? So whenever we are doing some operation, we are choosing two indices L and R and removing all the elements in between. So j is equals to 1 means I want to include this ball at the ending of the sequence, or you can also say I want to make this index make this the right index of an operation, right? You can like say it in both ways. Now if j is equals to 0, that means I don't want to do anything with this index, right? So this is as simple as it is. So let's say now I have this particular part. I have clearly defined what is my dp of ij. So whenever I am trying to calculate dp of I0, so this is very simple. I just have to take the maximum of dp of I minus 1, 0, right, and dp of I minus 1, 1. So why is this so? I don't want to do anything to the current index, so it will not affect my answer, right? That is very clear. And I just make a transition to the I minus 1th element. Now either I minus 1, 0 will give a good answer, or I minus 1 will give a good answer. I don't know. So I'm going to just take the maximum of both of them, right? So this part is clear. Now what happens when I want to include this particular index as the ending of any range, right? So there are actually two ways to solve this particular problem. So let's say there are some elements like this, right? So these elements are equal. So let's say there are some elements like this. These are all 2, and there might be some elements in between them, right? And let's say I'm at this particular index, right? So I want to calculate, or I want to include this particular index as the ending index. One of the ways is to take this particular range, right? One of the ways is to take this particular range and delete it. So the answer in this case will be the size of this particular range, because these will be the number of balls I remove, and the answer of this particular range itself. So let's say this position was lost, right? So if I include this particular range, my answer is going to be dp of last minus 1, and again I'll have to take the 0 and last minus 1, 1. So I'll have to take the maximum of both of them, right? So this is the answer given by this particular range plus the size of this particular range, right? So what I'm essentially doing is I'm considering to remove this particular range. Now when I consider this particular range, my answer will be equal to size, because this is the size of this particular range, and this is the value that will be added to my answer. Now I'll also add what is the answer that my remaining range will give, right? So this will be given by the maximum of these two values. Now this is one way of doing it. The other way can be, let me just rewrite those values. So there will be obviously some values in between, right? The other way can be, I don't want to delete this range. Instead, what I'll try to do is, I will try to extend this range, right? So what do I mean by extending? So let's say there is some range that ended here, right, at this particular index, right? So one way we have already discussed that we included the last 2's, right? Now what we do is, instead of ending the range here, I am just trying to extend the previous range. So let's say the previous best range was, I was trying to end at this particular position, and this range was the best answer, right? So now what I do is, I try to extend this particular range. So instead of including till here only, I include this element also, right? So the answer in this particular case will be size, right? And this time the size is different. The last time what we did was, the size was the elements between including these 2's, right? Now I will not include this particular 2, I will only calculate the size till here, because this would have been already calculated previously, right? So now I take this particular new size and dp of last. So you see what is the difference between these two approaches. So that this is case 1, and let's say this is case 2, right? So in case 1 we were removing the last 2's, right? We were considering them as a range and we were removing it. In this particular case, I am not removing this particular 2. Instead, I am just trying to figure out what was the best range for this secondary 2, right? I am just trying to figure out what was the best range for this 2, and I am trying to extend this particular 2 with the same range, right? So how will I know what was the best range for this particular 2? I will know it by dp of last and 1, right? So I considered I would end this particular range, and this answer, the best answer would be stored at dp of last and 1, right? So my dp of I1, we have already calculated dp of I0. My dp of I1 is going to be the best of these two values, this value and this value, right? So we have discussed how we can end. So this is 1 actually. So we have discussed how we can end that particular index I. Now at the end, what will be our answer? Our answer will be maximum of dp of n0 comma dp of n1. So let me just quickly go through. I know this explanation was a bit lengthy, so I'll just quickly go through what we are doing here. So we are introducing a DP of ij, and I will denote the ith ball. J will be of size 2. When j is equals to 1, this means I want to end any particular range. I don't know what range it is, but I want to end any range at this particular index I, right? So this particular index I will be the right end of my range, right? This is what j is equals to 1 denotes. Now if j is equals to 0, that means I don't want to do anything with this index. I do not care about this particular index. So if I do not care about this particular index, my answer will be maximum of dp of I minus 1. There it can be also 0, there it can be also 1. So I have to take the maximum of both of them. Now if I want to end my range at this particular index, there are two ways to do it. Now what are those two ways? One way is that I take the previous two and create a range like this with the current 2 and the previous 2. So if I do it, then my answer is going to be dp of last minus 1. Last is the position of the previous 2, right? So my answer will be maximum of the remaining values. So for the remaining values, I'll have to consider both 0 and 1. That is why I take the maximum of both of them. And the size. The size is the size of the range including these two 2's, right? So now the other case is I do not include the last 2. Instead of like starting the range from there, I'm trying to deal with the range that started previously, and I'm just going to extend it, right? So how do I extend it? I try to find what was the best answer for this particular position. So that will be student dp of last comma 1, right? And I add the size to it. So this will be my answer for dp of I1, right? At the end, I'll just have to take the maximum of both of these cases. Now my final answer will be student dp of n0 comma dp of n1. So let us have a look at the final code, what this code looks like. So you will see what I've done is I've created a integer n, and I've taken a vector v of size n plus 1. So basically I'm doing all of this for just one based indexing. Similarly, I've created a positions vector. So this will store the last encountered position of any element. Since all the elements were up to n only, right? So that is why I can also create it for n plus 1. And dp is also of n plus 1 cross 2, this array or this vector. All of it are one based indexing, right? So position array is going to store the last position of the similar element. Now I just traverse through all the elements, and dp of I0 will be definitely equals to I minus 1 0 and dp of I minus 1 1. Now if position of v of I, that means the last position of this particular element is not equals to minus 1, then I'll update my last as position of v of I, right? So I'm just checking the last position. Now there is one case when I try to start my range from the previous index and end my range at the current index. So in that case, my total size will be I minus last plus 1 and maximum of dp of last minus 1 0, dp of last minus 1 1. Now if I don't include the previous element, but instead I try to extend the range, then my size will be only equals to I minus last, because this time that particular previous index would have already been included in my answer, so I don't need to include it again, plus dp of last 1, right? And for the current dp of I1, I take the maximum of both of them, and I update my position of v of I as I, right? After it, I can just at the end print the maximum value of n0 and n1. This would be the solution of the third problem. Now coming on to the fourth problem. So I just hope that we don't get any failed system tests on this particular problem. Otherwise, like my rank will degrade by a lot. Anyways, we are going to discuss the solution which has passed the pretest, and we are hoping that it also passes the system tests. So anyways, what this question says is we have n animal friends, and we have numbered them from 1 to n, right? So there is one animal, that is the animal 1, which must included in all the games, right? So I'll tell you what is the game in a while, and the animal n should not be included in any of the games, right? These are two conditions, and there are some extra conditions as well. So each of those conditions will be denoted by like this: ui, vi, yi. Now this the statement that they have written here was a bit complex. I had some trouble understanding it, but I'm just going to tell you what the statement overall means. So if you have been given three values ui, vi and yi, so let's say in this particular example it is 1, 4 and 2, right? So the total time you play with 1, in this particular case the total time you play with 1 and not play with 4, remember this line, the total time that you play with 1 and not play with 4 should not exceed 2, right? Not exceed 2 means it can be equal to 2 but not more than 2. Now similarly, the total time you play with 4 and not play with 1 should not exceed 2. Similarly, it is the other way around. That means if you are playing with one of them and not playing with the other of them in this particular pair, this particular time should not exceed the total time that has been given to us, right? So basically we want to play some games with them, right, with these animals. Now we can choose a subset of n animals. Subset means we can choose any number of animals from it, and they can be any one of them, and we can play a game with it, right? And we have to play a game such that the first element is always playing and the last element is never playing, right? And we have these conditions as well, these extra conditions that we have to take care of it. So at the end we will have to tell what is the maximum amount of time that I can play games with my animal friends, right? So they have given an example like this. Let me just show you, explain you with this particular example, right? So you will see that we have some values here. Now they say that 1 and 3, right? 1 and 3 means if only 1 is playing and 3 is not playing, right, this total time should not exceed 2, right? So let us see how we can do it. So 1 will always be playing, right? So they have written 1 0 0 0 0. So these are 5 animals. So 1 is playing for 1 unit of time. 1 is playing for 1 unit of time. So now they say animal 4 comes and they together play, 1 and 4 together play for 1 unit of time. So this is 1 and this is 0. So there were two conditions related to 1. So one was 1 3 and the other one was 1 4. Now you see that for this first condition, right, 3 has played 0 number of times, right? 1 has played 2 number of times, right? 1 here and 1 here, right? Now I cannot write another game in which 1 is playing as 3 and 3 is not playing, right? This is what they mean by the conditions, right? So now the next game, in the next game, what they have is 1 is playing and 3 is playing. So that's acceptable. 1 is playing and 3 is playing. Now you will again see this is 1. Now you will see that the player 1 has played a total number of 3 times. But the number of games in which 1 was playing and 3 was not playing, let me write it like this. This is equals to 2. The number of games in which 1 was playing and 4 was not playing is equals to 2. Right. So this one, the first game and the last game is the game in which 1 was playing and 4 was not playing. And the first game and the second game is the game in which 1 was playing and 3 was not playing. So now any game I make, I need 1, 3 and 4 all of them to be present together. Otherwise I cannot play a game. Because if I write 1 and 4, let's say, so 3 will be sad because we are playing more than 2 games in which 1 is present and 3 is not present, right? So we have to take care of these conditions. That is why for the next game that they have, they have playing players 1, 2, 3 and 4 playing, right? So the problem statement written there was like a bit confusing. So that is why I explained this problem properly. And now let us have a look at what they have to say here. So they are also given an example where friends 1 and 2 play for 1 more minute. So if I play with friends 1 and 2, right? So if I play with friends 1 and 2 now, for example, 1 is like this, 1 is like this, and the others are 0, right? So in addition to violating these first two conditions, right? We already know we are violating these two conditions. We are also violating this particular condition now. Why? Because 2 is playing and 3 is not playing, right? So this was just one more example to make you clear that what is the problem statement saying. Now, 1 will always be playing. You will see that this problem somewhat looks like a graph. So let us make a graph out of it. Now let me just write it as node number 1 and it is connected to node number 3 and 4 by 2. So let me have node number 3, node number 4, this is 2 and 2. Now we have 2 is connected to 3 and 2 is connected to 5 both by 1 and 1. So we have 2 here, 2 and 3 connected and 2 and 5 connected and both of them are 1 1. Right. So this is the graph that we have. So it is not very difficult to visualize what are the maximum number of games I can play with only player 1, right? So if I have only player 1, I want to play the maximum number of games I want, that will be equals to 2. Why? Because if I calculate the minimum, of all the edges that 1 is connected to, that will be equals to 2. Why am I calculating the minimum? Because I can only play 2 games. Why am I calculating the minimum? Because I can only play 2 games such that I am playing with 1 and the other elements are not included or its neighbors are not included, right? once this limit of 2 is exhausted, then I will have to include 3 and 4 as well, right? I cannot leave them alone now because this limit has been exhausted. So my basic idea is to greedily try to exhaust this particular limit, right? So if I exhaust this limit once, then only I can include their friends. So let's say now we have included 3 and 4 as well. I tried to play with 1 alone and I was able to play 2 games, and now I have to include 3 and 4. Now since I have included 3 and 4, now I have to check all the neighbors of the players that are playing now. So I have to check the neighbors of 1, check the neighbors of 3, check the neighbors of 4. Now such 3 and 4 are included. I can only play one more game, because if I play the game with 1, 3 and 4 together, I can only play one more game such that 3 is playing and 2 is not playing, right? So I can play one more game and then I will have to include 2 as well, right? So all of them will be included now, right? And this was also 1. So I can play one more game such that 2 is playing and 5 is not playing, right? So let's say one more game is included. Now at the end I will have to include 5. But since the problem statement says that we don't have to include 5 ever, we don't want to include the nth animal, so that is why the operation or the game will terminate here and we cannot play any more games, right? So I hope that you were able to understand what we are trying to do here. We are just trying to greedily find what is the minimum number of elements or what is the minimum number of games I can play with the current state. And if I cannot play any games further, I try to include more elements, right? So this was a very simple example. This will not help you to visualize the correct implementation of this particular problem. So let me just try to complicate this a bit. So let's say this is 4 and this is some node. I'm just not numbering it right now. So let's say these were 2 only. This is 2, this is 2, and let's say this is 10, right? So this is node 1 now, the central node, right? So we are starting with node 1. You would have easily observed that the minimum now 2, 2 and 4 is 2, right? So once I play 2 games, let's say there are some players like this. There are 1, 2, 3, 4, 5 players. So I just played 2 games with player 1, and that is when I felt that I need to include these 2 animals as well now, right? Now you see that this distance is 10 and I have already played 2 games with 1. These 2 elements are now included, these two, and this one also is included now. These 3 animals are included. Now what is the next number of games I can play? Earlier it was easier, we were just keep on expanding and we were finding the minimum value. Now how do we find the minimum value in this particular case? You will need to see that player 1 is still playing, right? And he has already played 2 games. Player 1 has played 2 games. Now to play more games, he only has 2 more games left. Why is it so? Because if he plays 2 more games, the total number of games will be 4. If this value becomes equals to 4, there will be 4 games in which 1 was playing and P was not playing, right? So that is why one thing we know, that we will also have to keep a count of the number of games that any player has played, right? We were earlier keeping a count or keeping a track of what are the players that are playing. Now in addition to that, we will also need to keep a track of all the number of games that a player has played, right? So whenever we are trying to find the minimum value, how do we actually find the minimum value? So let me just write here, whenever we are trying to find the minimum value, what we will do is, these are the steps, right? We will look at all the animals that are currently playing, right? For all those animals, we will have a look at their neighbors, right? And among all those neighbors, I want to find the value of among all those. So this is point C. There's neighbors. I want to find the minimum value of let's say this is the WT is the value that they have, and minus played of the current node, right? So played of current node is the number of games that the current animal has played, right? So basically, if I'm at node 1 and I have explored these two nodes, let's say this is 1, this is 2, this is 3. I've explored 1, 2 and 3, right? These are the 3 players that are playing a game now, right? So let's say player 2 and 3 have played 0 games and player 1 has played 2 games. So now I will look at all the available neighbors. So player 2 has this particular neighbor, player 1 has this particular neighbor, and player 3 has no neighbors. So player 1 has one neighbor, right, and its value is 4. So I want to find the value of 4 minus 2. Why? Because 4 is the maximum value, the maximum difference that we have. 2 is the number of games that 1 has already played, so he can only play 2 more games, right? Now here in the case of node 2, it has already played 0 number of games, right? It can play 10 more games such that 2 is included, and this, let's say this element 5 is not included, right? So this is how we are going to calculate the minimum number of games that we can play. The minimum number of games we can still play such that no condition is dissatisfied. Now when we have found the minimum number of games that we can play, we will play with the current players. We know what are the current players, we will play that number of games with the current players, and for all these nodes that we will have to include in the next exploration phase, we will include them, right? So this is what we are going to do. Now when will our answer be infinity, or when will this particular loop will break? Whenever we encounter this particular node, fifth node, since we cannot play with him, we will break from here, and this is the end of our loop. And whenever we have encountered a node such that it does not have any minimum value, right? Let's say this was the node 1 and it is not connected to any other nodes, so it does not have any constraints. Or let's say this was connected to some node. Let's say this was the node 1 and this is connected to node 2 and there was a value 3 here. So we can have 3 games like this where 1, 1, 0, 1, 0, right? It is like this. Now 2 is not connected to any other nodes further, so all the other games can be like this 1, 1, 1, 1, 1, 1, right? So in this case the answer is infinity. When the minimum value that we are trying to find, some minimum value, right? Minimum number of games that we can play, right? This is the whole step where we are trying to find that minimum value. So if we don't find any minimum value, that means we can play infinite number of games from here on. So this would be the solution of the fourth problem. So this was just an implementation greedy problem. Let me just directly show. That is why I wanted to show you the code. What how to implement this particular problem, right? So I've taken two integers n and m, and I'm creating a vector of sets. So basically this is going to store my graph, and each position of the vector will have a set of pairs of int, right? So why am I taking the set? I'm taking a set for two reasons. The first reason is I have to remove. So I just forgot to discuss this part. Let me just tell you about this quickly. So let's say from this particular node, first node, I know that I have explored this second node, right? So it is optimal to delete this particular edge. Why? Because I don't want any backward interference, right? Since I've already explored this node, I'm exploring this node, so I only want to look at the next neighbors. I don't want to go back, so that is why I was deleting this particular edge, right? That is why I've stored it in a set, so that deleting the edges is easier, right? And there is one more reason. Since I am finding the minimum values, so set will always store all the elements in sorted order, and that is when I'll get all the elements, and finding the minimum element will be easy, right? So I am creating a vector of pair, strings and int. So this will just basically store all the games that we have, and I am creating two vectors, current and play. So current is going to store the all the current players that are playing, and play is the number of games that they have played, right? So I am marking the 0th index or the first index as 1, because we know that the first player will be anyways playing. So all of the things that I am taking here is 0 based indexing. That is why you will see here I have also decremented a and b as well. So I create a while loop. So I've just set true here, because I'll be returning from in between the statements, right? I find the minimum value and I initialize it with infinity. Now I just traverse through all the nodes. I check whether current of I means I want to check whether the current player is playing or not. If the current player is playing and he has some of the adjacent neighbors, right? So the current animal is playing and it has some of the adjacent neighbors. I calculate the value. The value is going to be the element at minimum distance minus play of I, right? So this is the minimum difference that we can have. And if I do minus play of I, that means this is the more number of games I can play such that no condition is violated. And I calculate the value of minimum as minimum of current value comma minimum. Right. Now if minimum is equals to infinity, I find no value such that the conditions are violated. I can just directly print infinity and can just return from here. Now I create a string t and I create a vector of integers nodes. So this t is basically going to store what are the current players that are playing, and nodes is going to store what are the next nodes I want to visit, right? Or what are the next nodes I want to include. So I just traverse through all the nodes again and I check whether the current player is playing, and if he has some of the adjacent nodes, and if the distance with the first node is equals to minimum plus play of I. So basically I was calculating here the distance of the first node minus play of I. Now I'm just adding it, I'm just doing the reverse just to find that this is the same element that we had. So we found the minimum distance with some element. Now I'm just rechecking whether this is the same element that we had calculated the minimum with. Right. Now I calculate the value of the child, right, or the next node that I have to explore, and I calculate the weight. So this was the original weight. For calculating the minimum number of games I can play more in the current state, I subtracted this play of I value. Now I am adding this play of I value again just to get the original state what was there in the graph, or just to get back the original information that is stored in the graph. So why am I doing all of this? There are two reasons. First of all, I have to push back the child or the new node that I have to explore in the nodes vector. And the second thing is I have to erase both of them from their respective positions, right? So from the parent, I am erasing the first position. This was easy, but from the child, I will have to erase w comma I, right? So for the parent, it was easy to remove the first node, but for the child, why I have to do like this? Because for the child, this might not be the first node that it has. It might also add some smaller nodes, right? So that is why I have to calculate this first value of w and I, then only I can erase it. And you will see I am creating a while loop here. Why while loop? Because there might be multiple children that were giving the same minimum value for any node. So I have to remove all of them and add all of them to the nodes vector. Now, if the current player or the current animal was already playing, so I add the value of minimum to it. That means it has played minimum number of games more, this value, right? And I add 1 to t. So t is going to store the current players that were playing or the current animals that were playing. Otherwise, if it was not playing, I just mark t as false. So now what I do is I just push back the value of t and minimum in the games array, right, or the games vector. So t is the players that are playing and minimum is the minimum number of moves that I can make. So I increment my answer with minimum. Now I just traverse through all the nodes, and if the new node that I have to add is equals to n minus 1, that means I cannot play my game anymore, and I just write go to end. So end is here. Otherwise what I do is I just mark current of I as 1. That means now this particular player or this particular animal is also going to play. Now at the end I can just print my answer value and the size of the games vector, and I'm just printing all the values in the games vector. This was all about today's contest. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and do share your comments or any general thing you would like to share in the comment section, because your engagement with this particular video really helps the YouTube algorithm to understand that this video was actually helpful for you, and it will be able to reach more number of people like you who want to keep solving new problems. So I see a lot of people who watch these videos have not subscribed yet. In case you are one of them, then definitely consider subscribing and share this channel with your friends. Till the next video drops, keep coding, stay safe, bye bye.